All right, guys, here is 13.4 notes. They go along with your packet notes. And if you need to pause, stop, things like that, please do so. Phase changes. We have talked about this first semester. You've also done it in middle school, but we're going to go a little bit more in depth. We're going to talk about how those particles are acting. What are they doing as they change phases? All right. So first off, just as a general brief overview, liquid to solid, solid to liquid. Okay. First of all, liquid to solid, that means it is losing energy. Okay, so here, this side is losing. Okay, this is gaining. And you guys know, oh, I did not spell that right. You get the general idea. But liquid to solid and solid to liquid, again, you know these. All right, so we just have freezing and melting. All right, and again, we'll talk about kind of what are happening to those particles. Well, if they're losing energy, freezing, they're getting closer and closer together. They're making that solid. Whereas the liquid, solid to liquid, the other way, they're gaining energy so those particles are able to move more. And they are spreading out a little bit farther, which that would represent a liquid. They're able to move, they're able to flow. Okay, so the next type is liquid to gas and gas to liquid. All right, so liquid to a gas, they're getting farther and farther apart. Those molecules are able to move more. They are gaining energy. Okay, so here they're gaining energy. All right, whereas gas to liquid, they're losing energy. Okay, so gaining energy, they're getting more momentum, they're spreading farther apart. You guys know this as, sorry that that keeps coming off, but you know this as vaporization and condensation. Okay, this should be familiar terms. So liquid to gas, vaporization, gas to liquid, condensation. All right, then the last one is solid to gas and gas to solid. Right, solid to gas, this is gaining a lot of energy. I'm going to see if I can write over here if it will stay. I'm just going to put gain energy, GE. Whereas gas to solid, they lose a ton of energy. Okay, so lose energy. All right, and if you think about it, it's all about the spacing of the particles. How far apart are they getting? All right, so again, solid to liquid, this is called sublimation. All right, so you might not know that. And deposition is the other way. So those are two that you probably are not as familiar with. So I'm just going to write along the edges. This is gaining energy. This one loses energy. Okay. On the other side, gains energy, loses energy. Okay. So then, remember with gaining and losing energy, it's about how much those particles are moving and things like that. Okay. So what is the difference? You've heard of evaporation, and you've also heard of vaporization. Well, what is the difference between them? Vaporization is the conversion of a liquid to a gas. Okay, that is our most common term that we are going to be using. All right, vaporization, liquid to gas. Evaporation is a little bit more specific. It is a non-boiling liquid. So this would be evaporation is like water from a lake. You're not boiling it at all. You are it's just turning from a liquid to a gas. Okay? And it's probably because of bonds and all that kind of stuff, which we will get into a little bit later. So evaporation, we use it as a cooling process. All right, so sweating is another example of this. All right, you sweat, all right, when you look at your head, you are seeing that sweat coming off. Okay, it usually looks like steam, but that's cooling you off. Okay, so what's the difference between evaporation and boiling? Well, evaporation is just at the surface level, all right? Whereas boiling is throughout the whole entire thing, all right? So bubbles, you will see that. Um, with boiling, whereas evaporation, you're not going to see those bubbles, okay? Bubbles aren't going to be formed. Vapor pressure is less than atmospheric pressure. So the pressure that is right above the liquid. So if we look in this picture, this right here, this is our vapor pressure. If this is less than the atmospheric pressure, it's not going to boil, okay? This pressure here, though, these are causing a lot more pressure on that liquid than the surrounding atmospheric pressure. So that's going to cause these bubbles in here to boil, right? So just the biggest difference, evaporation is just at the surface, okay? Whereas boiling is throughout the whole thing. All right, so what is vapor pressure? It is pressure that's exerted by a vapor over the liquid. So what are those vapor, those gas molecules? So how much are they pushing down on that liquid? Remember, pressure is all about a force exerted over a surface area. All gas molecules have that. Okay, so how much pressure is being exerted? Boiling point, though, is a little bit different. Okay, we're going to talk about it in terms of kinetic energy. All right, and so with kinetic energy, it's the particles have enough energy to vaporize. They are getting enough energy to move from that liquid stage to that gaseous stage. Okay, so they're then going to vaporize. Okay, in terms of vapor pressure, though, it is where the vapor pressure, so those gases that are right above that liquid, equals the external pressure of the liquid. What are they pushing on that atmosphere? All right, so boiling point, you can look at it in energy and in pressure, so in vapor pressure. So vapor pressure is just all when it equalizes each other. Okay, so here again with the picture. So boiling point is where now all of those particles are able to escape, or where they're starting to escape. Okay, where do they have enough energy to overcome that atmospheric pressure? Okay, where can they start getting released into that atmosphere? All right, so at higher um, elevations, pressure's a lot lower. There's not as much things pushing down on that liquid. Okay, so it's going to boil at a lower temperature. It doesn't have to overcome as much. It doesn't have to equal as high of a number to overcome that. It doesn't have to overcome as much atmospheric pressure. Okay, because atmospheric pressure is lower, so vapor pressure will have to be lower. So boiling point is lower. Okay, all because of the amount of particles that are pushing down on that liquid. Okay. These affect cooking time, so you see it on baked goods. You see it on everything that you make. Any package, it usually says something about higher altitude. Okay, so at normal boiling point, the boiling point of a liquid is 101.3 kilopascals. Okay, if we look at pressure, that's what it's at. Okay, so this leads us to our last little bit called a phase diagram. All right, so if you notice with this phase diagram, there are 3 different spots. Okay, so we have our ice, we have all 3 of our phases, liquid and gas. All right, so all of these lines, so this line right here in green, that is where we go in between a gas and a solid. So this is where sublimation and deposition occur. Okay, the red line that I'm going to draw is in between a liquid and gas. Okay, so here, going across here, this is where boiling and melting occur, or no, boiling and condensation occur. All right, the blue one is in between solid and liquid, so this is where freezing and melting happen. Okay, and we have to take into consideration temperature, all right, which is probably the one that's the most common to us, and then pressures along this axis. Okay, so we're always going to look at, okay, if I am at 1 atm and 100 degrees Celsius, well, right here, okay, that is where water boils, okay, or water turns back into a liquid, okay? We know that, all right? We can go through any one of these spots and figure out, okay, well, where is it going to be boiling? Where is it going to be melting? All that kind of stuff. You just look at pressure and temperature because they both go hand in hand on figuring out phase. okay? Because remember, pressure deals with the amount of energy, how much are things pushing on it, which tells us how those particles are interacting. All right. I can also say, all right, well, I'm at, maybe I'm at 0.5 ATMs. So I'm right here. And I'm at like about 25 degrees Celsius. So right here. So I know that water is going to be in its liquid stage. Okay. I can figure out, okay, when is it going to be a solid? When is it going to be a liquid? When is it going to be a gas? If I'm given a certain temperature and certain pressure, I can figure that out. Okay. There are some very key points. Right here is our triple point. All right, and you're going to get a definition for that here in a moment. But this is where all three phases are happening. Okay, right there. So we know the temperature and pressure of that. Okay. We also have what's called the critical point, which is all the way up at the top. And this is where after that, it's really hard for things to exist, or it might all exist as a gas along that point. Okay, so some definitions with that. Okay, the triple point that I was talking about, this is where all three phases can exist. And just remember that you have to be at that temperature and at that pressure for it to work. Okay, just as I said, exact temperature and exact pressure. All right, it changes. Phase diagrams are going to change depending on what substance you're looking at. Water is different from methane, which is different from carbon dioxide, which is different from all of these different. Any substance you're looking for has a different phase diagram. So triple point is going to change. Okay. Normal freezing and boiling point. This is always at 1 atm of pressure, or 101.3 kilopascals. All right, so normal boiling and freezing points, they're usually marked on the charts. Okay, and that is the end. Remember, if you need to go over this, make sure to watch it a couple times. If you have questions, let me know. And remember, use your book. 13.4 is a good resource to help out with this. Okay, so if you have questions, make sure you either email me or come in and see me. Okay.